It's my distinct pleasure to welcome you to what's become one of the must-see events of CES, the Mobileye annual press briefing, where we discuss the accomplishments of the prior year and set the technology agenda for the coming year in this very exciting field of vehicle autonomy. Before turning it over, I need to let you know that today's presentation takes place during Intel's quiet period before we announce our fourth quarter 2017 financial and operating results. Today's presentation may contain forward-looking statements. All statements made that are not historical facts are subject to a number of risks and uncertainties. Actual results may differ materially. Please refer to our most recent earnings release Form 10Q and 10K for more information on the specific risk factors that could cause actual results to differ. And now I'd like to turn it over to Mobileye's CEO, Intel's Senior Vice President, Professor Amnon Shashua.
Thank you, Dan. Good morning, everyone. So after yesterday night's keynote, I have to be very humility here. There's not going to be any show, no flashing, but I'll try to focus on the open problems, our achievements in 2017, what are our plans for 2018, what is really difficult, what is open, what is mature, and how we're moving forwards towards 2021 when we believe that we'll have autonomous cars, fully autonomous cars, level 4, level 5. So I'll start with summarizing 2017. So in 2017, we had 30 design wins. So we won 30 production programs, over 27 car manufacturers, but 15 of them are in China. So this is a year where our kind of penetration, and so we had China relationships, penetration over the years, but last year, 2017, was really a big step forward. In parentheses, I wrote that in 2016, we had 12 design wins, and 2016 was a great year. So more than double of 2016, and about 70 car models. In this table, you see that the features, all these features are very advanced features. Of course, AEB, automatic emergency braking, is now standard. It's almost in every program. But we have many programs with free space detection, programs with level 3 automation, programs with the traffic light detection, all very advanced. We don't see any more programs that are 1 or 2 features. It's all advanced programs. So this is in terms of program wins. In terms of product launches in 2017, we had a number of them. I highlighted on the left 3 of them: the GM Super Cruise, which is hands-free driving; Audi ZFAS, level 3 in limited situation, it's level 3. All of these are IQ3 launches, and the Nissan Autopilot was launched in the US after a very successful launch in Japan a year before. The Nissan ProPilot is camera only, just a single camera performing hands-free driving, and the reviews were raving, both in Japan and in the US. So those are the launches that we had in 2017. On the right-hand side, you see also the tier 1s launching with us. So all of these are IQ3 launches. In terms of IQ chips shipped, we had an increase of 45%. So in total, we have 24 million chips out there, so 24 million cars on the road with our technology. In 2017 alone, around 9 million, 8.7 million IQ chips were shipped, which is a growth of 45% compared to 2016. What's happening in 2018 in the area of driving assist? We have 15 programs to be launched during 2018. If we compare this to 2017, where we had 6 program launches. So we have 15 program launches in 2018 across 14 car manufacturers. 4 of them are domestic China. 4 programs with IQ4, so this is going to be the first time that the IQ4 is being launched in serious production. The chip already exists for the past 2 years, but the serious production launch is happening this year. So 4 programs with IQ4 and 12 additional starting from 2019. So we have 16 design wins for IQ4 with the different car manufacturers. 2 programs with a trifocal camera configuration, so it's not just mono, it's 3 cameras with varying fields of view and performing very advanced functions. And all the programs have full feature bundles. So very, very high-end. High-end meaning also the ASP, the average sales price, is relatively very high. New features that will be launched in 2018. Our vehicle detection is moving towards a 3-dimensional description. It's a 3-dimensional box surrounding a vehicle, even though it's a monocular camera. We have been showing that for the past 2 years, and in 2018, it's going into serious production. Traffic light detection is in serious production. Traffic light is a very tricky feature, because it's not just detecting the traffic lights. It's also detecting the relevancy of each traffic light, which traffic light is relevant to what direction, and that is very tricky. It changes from geography, from country to country. There's a lot of, it's like traffic sign recognition. There's a lot of support work that needs to be done in order to make this work in serious production. And then advanced road features, the semantic free space that I've shown last year, holistic path prediction, all of these are going into serious production. And the biggest highlight is that REM, our crowdsourcing technology for creating maps, is going into serious production 2018 with 3 car manufacturers. So this is summarizing 2017. Now in terms of strategy, I'll kind of highlight our philosophy of a strategy moving forward. So the first philosophy is that we see the entire activity from level 2, which is today's driving assist, to level 5, which is fully autonomous cars without a driver. We see that as a single effort. We see that as a single effort because we would like technologies that we develop for level 4, level 5 to see their derivatives propagating downwards to level 2, level 3. We also initiated a new category that I'll explain later, which we call level 2+. All this trickling down of derivatives of technology is very important because at the end of the day, we're not a university, we're not an academic institute. We need to build a business. And putting all the eggs in the basket of some point in the future, level 4, level 5 will start generating big income, which I believe it will, it could take an amount of time. We would like to see those derivatives of the technology starting generating income today, and not just when fully autonomous cars are driving on the roads. So we see that as a single effort. We don't want to see a piece of technology being developed for level 4, level 5 that doesn't have any use today. If we don't have any other way to do it, then of course we will do it. But if there is a way to put a technology for level 4, level 5 that has a use today, it's much better than putting a technology that doesn't have a use today. So the philosophy is a single effort. Another philosophical element is economical scalability. Right? We want to make sure that our activity in level 4, level 5 automation is not going to be a science project. And my feeling when I look at the activities of our colleagues in other companies, I would call this more a science project than something that is geared toward really serious production. And we want to make sure that our effort is not going to fall in this bucket of a big, expensive science project. So economical scalability is key, because if you are developing a product that does not scale geographically, does not scale in terms of cost when you start reducing cost, when you have more and more vehicles to put on the road. We would like to build a technology in which you can manufacture millions of cars and not 100 or 1,000 test cars. So economical scalability is a big issue, and one of the key elements in economical scalabilities are the maps. The high definition maps is a logistical problem, and the crowdsourcing approach helps us to remove that element from the cost structure of building an autonomous car. There are other expensive components like computational demands behind planning, behind driving policy. The classical way of doing that explodes exponential with the number of vehicles around you and the time horizon that you need to plan. We have techniques that avoid this exponential explosion. So it means that that the computational cost that we'll need will be much lower than what people believe. And then scalable and a workload diverse system on chips. So we need also hardware to accompany the software. So it's all about economical scalability, right? It's economical power consumption, economical system on chips in terms of cost, economical algorithms in terms of the explosion of computation, the density of computation, economical map building, economical sensors. Everything has to scale. If it doesn't scale, it's going to be a science project. And the third one is safety. And I would say that when people talk about safety, people mean different things. And what we mean about safety, it's not the probability of a bug, of a software bug, or probability that you'll have a hardware failure, a sensor failure. We're talking about something more realistic that is very likely to happen, that your vehicle simply made a mistake, simply made a wrong decision, changed lane, was not supposed to change lane, cut in another vehicle in a dangerous situation, and an accident happened. An accident happened not because there was a bug. And this is much more likely than an accident happening when there is a bug. Because today, the safety industry, it's called the ASIL, which is system integrity, has a good way to handle protecting against bugs, against the integrity of the hardware, software. But we are talking about something completely different. We have multiple agents on the road. Each agent perceives the world, and even if the world is perceived in a perfect manner, there is decision-making to make. You need to merge into traffic, and those decisions can create accidents. How do we make sure that accidents will not happen? And this is a big issue. It's not only a technological issue, it's also a logistical and regulatory body issue. And we started to reach in that area during 2017, and I'll be more specific as I go along. So again, all these components, economical scalability, safety, and having a single effort is what is driving us forward. Again, our purpose is not a science project, but something that goes into production, like our very successful field of driving assist. So just to remind the three areas that are critical when you want to build an autonomous car, it's sensing, there's all the cameras, radars, laser scanners, the high-performance computing that computes the raw signals coming from those sensors, and creating an environmental model. Detailed description of all the useful information around the car, the road users, drivable paths, traffic signs, and so forth. The second part is mapping. You need high-definition maps in order to create redundancy, in order to create foresight, so that you can know where the drivable path heads to, even beyond where sensing tells you. And the technology and logistic operations on how to build and update these maps. And the third one is driving policy, making decisions, planning ahead, merging into traffic, all the stuff that we learn when we take driving lessons. So those are the three areas. And in all of them, you have lots of artificial intelligence and sensing, being able to interpret visual signals, the object recognition, the interpretation of the road signals, the drivable path. It's all full of artificial intelligence. The driving policy, the decision-making is a lot of artificial intelligence, what is called reinforcement learning. And building the maps, we use artificial intelligence of sensing in order to build the maps automatically. So in terms of sensing, we see two areas. One is quite mature. It's not easy, but it's quite mature. And the second one, that there are lots of open problems there. So the mature part is detecting road users and objects that are compact, that you can put a bounding box around them. So these are vehicles, pedestrians, and cyclists, but also traffic signs, traffic lights, everything that is compact in the frame, where you can put a bounding box around it, and you use techniques of object recognition to identify that particular area, region in the image, is quite mature. It's part of driving assist, it's in serious production. As I mentioned before, many of those things are in serious production or coming in serious production this year. The second part is parsing the roadway. It's understanding the lane marks, the road edges, the path delimiters, where we have curbs or we don't have curbs, the drivable paths, and the semantic meaning associated with the drivable paths. And this is largely an open problem from a perception point of view. So you want to be able to detect all this information, first to create a redundancy between a map and sensing. And second, you would like to be able to detect all this kind of information in order to build maps in the first place. Because these are the building blocks of building maps. It's not only the building blocks of controlling the car, it's the building blocks of building the maps. And we would like to build the maps automatically. Therefore, we need technology to be able to identify this information from the scene. And I'll show you a few clips how complicated it is. And this is a real focus of 2017. And I think we have very, very good progress in that area. So let me show you a few clips in that area. So what you're going to see in this clip, I'm just going to show the road edges, an edge between a road and a physical barrier, which could be a curb. So it's not going to show where the lane marks are, but where the road edges are. Basically, it provides a boundary of the free space that you can drive, and I'm going to show this in urban setting. So if I stop this here, you can see this red line. This is a curb, and it kind of engulfing the curb in the right manner here and here. Okay, if I stop this here, you see the same thing. This is a boundary. This is a curb. Okay. And you can start appreciating the complexity of this, because when you look at this area, for example, there isn't much difference between the texture on the sidewalk and the texture on the road. It's really identical. So the reason that the algorithm was able to put a line here and say this is a road edge, it is because of holistic processing. It's processing of the entire scene and not just a local area. And this is where very sophisticated deep networks are coming into play. Okay. And this kind of road edge detection is part of 2018 launches, or one of the 15 launches in 2018. Let me show another. Again, all of this in urban traffic, which creates a very, very challenging. Let's go here. You see here the curb, the line on the curb. There's another curb here, a curb here. So this is being processed from a monocular camera, single image processing. And you can see that the texture information in the scene is very complex. Being able to identify only the relevant information and doing it robustly is very, very challenging. We have been working on this for quite a while. It's an evolution of a number of years. And it's going into serious production. Here we're putting things together. So this is the 3D video. Every vehicle, there's a 3D bounding box around the vehicle. You have also cyclists and motorcycles, but also stationary objects. You'll see in a moment some stationary. And the red here is the road edges. The yellow rectangles on the side, which in a moment you can see. Let me stop it. Okay, so these are all stationary objects. At the moment, these are trunk of trees or poles. It's also being detected as part. Right? So this is part of a sector environmental model. Right? So this is a sector, meaning this is what a single sensor sees, and parsing of the visual information in terms of path delimiters. I'm not showing the lane marks, mostly because in this clip you hardly see any lane marks. The road edges, stationary objects, and all road users in a very detailed manner. And this is a sector, and then you take different sectors when you have a 360-degree coverage, and you create a complete environmental model, and then you have laser scanners and radars, and you fuse them together for redundancy. Here's another a nice piece of technology. This is when you don't see lanes. Humans can still see a path. We can do that as well. The information to the system, besides just the image, we know what the route is. So, and we display this as two lines telling us where, if we reach to a junction, where are we going to go, right or left. So as you see here, this is the blue line is the projection of where the path should head, even though we have no lanes at all. Right? This is important not only for sensing, enabled to do vehicle control when there are no lanes, but also for map building. Right? People would like to know where the path is as part of building a map. Okay. So this is about sensing. Let me go over the process of building maps, and then now I also want to focus on what were our achievements during 2017. So the process of building maps is using crowdsourcing. We're leveraging the fact that almost every new car comes with a front-facing camera, and most of them have a Mobileye chip behind the camera. So we have access to the crowd. So it's not only we come with interesting and innovative technology, we have access to the crowd, which is something that is difficult to achieve. So having access to the crowd, having software on our chip that can parse the roadway and the kinds of clips that I've shown you, this information together with landmarks are sent to the cloud, and in the cloud, it's all pieced together to create a high definition map. And when we talk about landmarks, and you see in this clip, we're displaying the landmarks. So it's everything that is stationary. It could be pavement markings, it could be poles, of course, traffic signs, traffic lights. All of this stationary information is used as landmarks for localization. So this is the technology. So we're leveraging driving assist. So the harvesters, the data collection is not coming from sophisticated vehicles with sophisticated sensors and sophisticated functions like level 4, level 5 autonomous driving. We're talking about the mid-segment cars, the low-segment cars, those cars that for the 4 stars and 5 stars ratings have a front-facing camera, they are the one who are doing the data collection. Okay? So leveraging the crowdsourcing automation, it will allow us to build these HD maps completely automatically. And since we're talking about millions of cars, we have a high density of refresh and building the maps. So this is kind of the general idea. And there are 3 building blocks, technological building blocks around this. One is harvesting, the data collection, and the data is packed into a 10 kilobyte per kilometer. So if you drive 100 kilometers, it's 1 megabyte of data, which is very, very small. If, say, you drive 20,000 kilometers per year, it's 200 megabytes. The cost of sending 200 megabytes, I don't know, it's less than $1. So the cost of uplink, the cost of sending the data is very, very minimal. The second piece of technology is aggregation. Once these packets, which we call RSD, road segment data, once these packets arrive to the cloud, we piece them together and update, build, and maintain the high-definition map. And then localization is software in the car as part of an application where the camera sees landmarks and matches those landmarks to the landmarks that are in the map, in this high-definition map, and provides localization at accuracies of centimeters. So these are the 3 pieces of technology. The harvesting is in the car, the localization is in the car, the aggregation is in the cloud. Okay? So let me show you 2 clips, or 1 clip. So what you see here, this is the projection of map data. All these lines are map data onto Google Earth. This is the same projection, but on the image frame of the car moving forward. So this gives you a sense of accuracy. If you look at this line here, it sits exactly on the lane mark. So it gives you the sense of centimeter level accuracy of the map data, but it also gives you a sense of the accuracy of localization. Because even if the map is accurate and you haven't localized the car inside the map accurately, you will not have an alignment between this line and the lane mark, right? So there are 2 sources of accuracy here, the map itself, which is built from crowdsourcing, and the localization. And you see all these yellow rectangles are landmarks that the system identifies and matches to the data stored in the cloud in real time. Okay, so this is how it looks like, and all this map was generated automatically. In terms of achievements during 2017, first we're preparing this harvesting for 2018 production with BMW, Nissan, and Volkswagen. So it's coming into production around 2 million cars starting from 2018, and there are going to be many more in 2019. We're preparing the roadbook. Roadbook is our name for the HD map, covering all of Japan highways. This is in cooperation with Zenrin, a Japanese map maker, and Nissan, for a level 3 launch in 2018, early 2019. So all of Japan, all of highways of Japan are being mapped, and I'll show you a clip of that in a moment. We have cooperation with NavInfo and Psych for bringing REM to China as part of our Chinese effort. And you know, in China, collecting data is very, very tricky. Controlling the crowd, controlling the data requires completely different logistical preparations. And part of it is a joint work cooperation with NavInfo and with Psych. We have deals ongoing with OEMs for harvesting 2018 and beyond, so it's not just the 3 BMW, Nissan, and Volkswagen. We have deals ongoing with car manufacturers for the high-definition map uses for a new category, which we call Level 2+, and I'll spend a slide or two on that. So it's a new ADAS category that will start in 2019, and it's a very, very cool feature, and I'll explain it in a moment. We are launching this month our new aftermarket device, which we call Mobileye 8 Connect. Our existing aftermarket device is based on IQ2, so it's relatively old technology, 2010 technology. This month we are launching the aftermarket with an IQ4 chip and with a modem. So vehicles with the new aftermarket will be able to contribute data as part of harvesting, and we have established a number of very, very interesting deals with fleets and with municipalities to install the Mobileye 8 as part of fleets and collecting data and providing data services as part of this, and I'll show that in a moment. And we're continuously mapping neighborhoods across the globe for supporting our internal efforts of level 4 development as a turnkey solution. So I'll provide a bit more information on all of this. So this is the part of the mapping Japan. So what you see here is all these lines. These are highways of Japan. All of Japan is being mapped, and it will be completed by middle 2018. All of Japan using this technology. This is part of this level 2+. So what is level 2+? So it's a new category. It says the following. Just to remind everyone the definitions. Level 2 is today's driving assist. The driver is fully in control. The driver is fully responsible. If there's a malfunction, the driver is expected to take control of the vehicle instantaneously. Now, we can argue whether it's good or bad, but this is how level 2 is defined. Level 3 is defined that the system gives the driver a takeover request of about 10 seconds. So if the system needs the driver to intervene, the driver has about 10 seconds to intervene. So it means that you need more redundancy. The cost of the system is much, much higher when you are starting from level 3. Level 4, there's no takeover request. You can go to sleep, but not all modes are covered. There are certain driving modes that are not covered. Maybe taking a left in a junction that doesn't have a traffic light would not be covered. It's called unprotected left. So there are certain modes that are not covered, meaning when you plan a route from point A to point B, make sure that the route covers only the modes that the system is designed for. But if it is covered, then you can go to sleep in the car. There's no takeover request. This is level 4. And level 5 is all modes are covered. You don't need a driver at all. No need a steering wheel. Okay, so you can see that from there's a big jump from level 2 to level 3 in terms of system integrity. Because in level 3, the driver, there's those 10 seconds that the driver does not need to be responsible. And it's very, very tricky in terms of system integrity. But level 2 is where we are today. And this new category of level 2+ says the following. Level 2+, there are very nice features like adaptive cruise control and lane keeping assist that provides you hands-free for a short period of time. Could be 15 seconds, could be 30 seconds, where you have a hands-free experience, and there's also an ACC keeping a safe distance to the car in front of you. We would like to make a big jump in the performance of these functions by adding a very, very small cost to the overall system. A big jump would be that you can have your lane keeping assist work also inside the city where the lanes are not clear or they are not even well defined. You'll have a lane keeping assist also when the lanes are not clear, like in some of California roads with these box dots and bad weather, and The system availability would be lower. We would like 100% system availability also in these challenging situations. And of course, use the ability of traffic lights and the stop line of a traffic light in order to create a much better ACC as part of the ACC and lane keeping assist. So the question is, what is this additional thing that I need to add to today's driving assist in order to make a big jump in performance? And what we need to add is the map, is this high-definition map. Because the high-definition map contains the lanes that even if you don't see them, they are in the map. And all what you need is just to localize the vehicle inside the map, project those lanes onto the image frame, and then fuse it with your sensing. So even if your sensing is not that sure about where the lane is, it is in the map. So you can get a much better lane keeping assist. And also the map contains the traffic lights and the relevancy and so forth. So you can get a much better ACC. And the cost is minimal because our map, the bandwidth is very, very small. For example, if you take an area of 100 kilometers square, 10 by 10 kilometers, the size of the map in a city density of, say, Munich is about 4 megabytes. So sending that amount of information by tiles is not such a big deal. So it's a very, very low-cost addition to the way the system is today designed. So in this clip, you see on the right-hand side, this is the situation. You see, you hardly see lanes. So you'll not be able to activate any lane keeping assist in this kind of scenario. Both the curvature is very high. You don't see the path well. Even though the system, tries to make estimations, here is the green line of a lane mark, it's not reliable enough to create a good lane keeping assist in this kind of situation. But you saw here that when you project the map data onto the image, you have here the center of the path very, very clearly marked, also the edges. So you can activate functions much more robustly in very difficult conditions, also in inside city traffic, than without the map. Here's another situation, also inside the city. You have here lane detection, but the availability is not 100%. And what you have here, you are raising the availability to 100%. So this is a new category that will start in 2019, leveraging the fact that we build the map. And this is exactly the point that I said at the beginning of trickling down technologies that were designed for level 4, level 5, and we want to bring them down to today's features. The roadbook, the high-definition map, the crowdsourcing was not designed for this. It was designed to support level 4, level 5 automation, and even level 3. But what we're doing by taking this technology and saying, how can we use it today? And this is an example of such a desire. The aftermarket. How's the aftermarket playing in this field? Again, so I'm still in the RAM, still in building maps. We have contracts with car makers like Volkswagen, Nissan, and BMW for getting the crowd, uploading data. But we have also the aftermarket. Now, in terms of volume of the devices of our aftermarket, it's about 10% of our volume that we sell for OEMs. But every car that has an aftermarket system, usually these are fleets, they drive 10 times more than a passenger car. So we're talking about cars that can generate very interesting data because unlike us, where we drive to work and then most of the day the car stays in the parking lot, these people drive all day. It could be taxis, it could be fleets, it could be municipality vehicles. They drive all the day. So the data that they generate, even if though the volume is smaller, 10 times smaller than the volume of built-in cars, they can generate much more data. So these are our aftermarket. This is the current generations of aftermarket. It's based on an IQ2. We are launching next month what we call Mobileye 8 Connect. It has an IQ4 because we need more processing power to extract this information that is needed for building maps, and also provide more features as part of a driving assist, based on an IQ4 and a modem. Okay? And we have another unit where we take multiple such units and create a 360 degrees for long vehicles where they have big blind spots inside city traffic. So the kind of map services that we provide even today without using RAM, just ability to connect through a fleet management system, we call hotspots. We can put on the map places where there is an excessive amount of forward collision warnings against pedestrians, and provide municipalities with information where are the areas that are likely to contain, an accident is likely to happen because there are too many forward collision warnings with vehicles that were passing through that junction, through that area. Then on top of that, you can think of the camera as an intelligent agent. The camera can know where there are parking spaces, can tell you where there are infrastructure things that you need to fix, like a washed out lane mark that you need to repaint, or a traffic sign that has the fill. So in order to create a survey, infrastructure survey, this information can be extracted from the camera, sent to the cloud, and added to these hotspots. Okay? So this kind of information, we started a cooperation with the ESRI, which is an analytics, a geoanalytics company that take the information and put it on maps and serve municipalities. This clip is from their website. So what you see here, the system detects pedestrians, and all these pedestrians are then placed on the map. And you have here, this is Manhattan. Let me go up. And all these are hotspots, areas where there were forward collision warnings with the pedestrians. And then you can start going into more details at what time of day you had more hotspots. This is morning time, and this is afternoon. In what direction the pedestrians was moving when there was a forward collision warning. And all of this data, you can use it to find patterns, and find patterns in order to improve the infrastructure. Put another traffic sign at a place where it's susceptible to have accidents and so forth. Okay? So using this infrastructure that we have already built using fleet management systems, with the Mobileye 8, we can also send data to create our REM maps, our high definition maps, and create more mapping services. So these are partners that have already signed in, and those are the number of vehicles of the fleets that will be contributing maps. So you have Get Taxi is one of them. This is like the Uber and fleet, Uber and Lyft. For example, in New York, 2,000 vehicles. So these 2,000 vehicles, it's like 20,000 vehicles in terms of passenger cars, because they are all the time on the roads. Okay? And this is the timing of the launch. So everything is going to be launched in 2018. And these vehicles will contribute data for building maps in cities using our aftermarket branch. Let me now go to the final chapter, and this is about safety. And I would say that safety is the elephant in the room. When people talk about safety, they'll talk about system integrity, making sure that there are no bugs in the system, that there will not be an accident because of a software bug or a sensor failure. I'm talking about what I mentioned before. How do we make sure that there are not going to be any accidents? And the problem is that it's impossible to guarantee that there's not going to be accidents. For example, if this is our agent, our autonomous vehicle, and these are human-driven vehicles, and this human comes and tries to hit our car, this car can do nothing. You cannot escape the accident, right? So there are going to be accidents which are not your blame. And we cannot avoid that. But the question is, can we avoid accidents of our blame? And then work with regulatory bodies in order to carve that out. So because we cannot avoid accidents, then the common wisdom is to claim that self-driving cars should be statistically better than human drivers. And this is a problem. The first problem, that it's not feasible. It's not feasible if you want to reach the levels of a probability of an accident that will be acceptable to society. We believe it should be 3 orders of magnitude better than a human. And you can prove a very simple claim that if you have an event that happens per hour at a probability P, the amount of data that you'll need to collect, the amount of hours of data you need to collect is 1 over P. P is about 10 to the minus 9. So with human driving, the probability of a fatality per 1 hour of driving is 10 to the minus 6, 1 to a million. We want to be 3 orders of magnitude better, 10 to the power of minus 9. 1 over P is 30 billion kilometers. So you'll need to collect data over 30 billion kilometers. That's infeasible. And second, it's not transparent. What happens if there is an accident? How are you going to explain it? What are you going to say? It's a black box that was trained for 30 billion kilometers? Non-transparency is also a problem. So we have been working on it from a formal standpoint. We published a paper 2 months ago, and since then we're updating it. This is an update that was 18th of December. And this is looking at this issue of safety from a formal perspective. It's a model we call a RSS. And the goal is that we would like to formalize the common sense or the human judgment of common sense of driving, is to formalize what is dangerous, what is a proper response. Once we formalize these two, we can then formalize what it means to be blamed for an accident. And if we can formalize what is meant to be blamed for an accident, we can then design an algorithm that will make sure that an autonomous car would never cause an accident. And then work with regulatory bodies on the parameters of this model, such that there's an agreement between society and industry players. And then an autonomous car can be certified such that its decision-making, assuming that the perception is correct, that you perceive the world in a correct manner, your decision-making will never bring you to cause an accident. And it also puts ethical dilemmas in a formal context. Okay? So there are two major questions that you need to ask when you come with a model. One is soundness. So if we want to formalize what is meant by blame, soundness means that if there's a situation in which the model clears the blame from the agent, says that the agent was not blamed for the accident, then human judgment, the common sense of human judgment, should agree with it. If human judgment does not agree with this clearing of blame, it means that the model is not correct. So this is soundness. And the way to verify this, there's a NHTSA crash typology report that it covers 6 million accidents, and they grouped it into 37 scenarios. Those 37 scenarios, they cover 99.4% of those 6 million accidents. And when we took our model over those 37 scenarios, it was sound. That means it never cleared blame in a situation in which human judgment does not clear the blame as well. And second is usefulness. Around this model, you have to have an algorithm that is local in its decision making. So there's no butterfly effect that you make an innocent decision now that later in time will explode and cause an accident. So what is this RSS? Is we define what it means by dangerous situation. Now this is not trivial at all, because if you look at today's traffic laws or what we learn when we drive, there's no clear definition of what it means to do a unsafe or dangerous cut-in. You cut in, there'll be an accident, you go to court, and then you argue whether your cut-in was dangerous or not dangerous. There's no mathematical clear definition of what does it mean to be in a dangerous situation. So it's really an open field, because humans don't need accurate definitions. Right? We need this flexibility to interpret. This is why law exists. Law exists in order to interpret the law, right? If the law was very, very accurate, we wouldn't have needed for lawyers, right? Right. Let's think about it for a moment, right? But machines, right? We don't need lawyers for machines. That would be very, very bad, right? We need machines to follow mathematical rules. But when you talk about driving laws, these are not mathematical rules. So the first thing to do is to think about this from a formal standpoint. So define what means a dangerous situation, define what it means a proper response. And a proper response has parameters. These parameters needs to be vetted or agreed with regulatory bodies. This is an effort. This is why we also published our work and made it open so that we can start a conversation with regulatory bodies. And then we can guarantee that the autonomous car would never cause an accident, and also make sure that all of this is efficient. This is the usefulness, that there will not be any butterfly effect. And then we can separate comfort, the planning, which has a degree of whether assertiveness, aggressiveness, or more relaxed driving. This we call comfort. This would be used using data-driven approaches, reinforcement learning. Separate that from the safety type of decision-making, which is model-based. Final part of the strategy is to look at the hardware. Right? So I spoke so far about the software elements of building an autonomous car. I talked about sensing. I talked about the effort of building maps, what we can do with maps even today, this level 2 plus. I talked about the effort of putting safety in a model-driven manner. Now I'll talk about the hardware that comes together with all of this. So this is the family of our IQ chips. IQ3 is in production since 2014. I think the first car manufacturer was Tesla. It's a 0.25 tera operations per second running at 3 watts. IQ4 was sampled 2 years ago and starts in serious production this year with 4 production programs. This is a 2.5 tera operations per second at 6 watts. I put here a comparison to NVIDIA Parker, which is 1.5 tera operations, 15 watts, just to get a sense of power density, computing density versus power consumption. And the IQ5, which is going to be sampled in a few months, it is a 7 nanometer process, 24 tera operations at 10 watts. Okay, I compared it to Xavier and NVIDIA Xavier, 30 tera operations, 30 watts. With the IQ5, it's not just an engine which is a pure play in deep inference. When you think about the types of computations that you need to cover sensing and mapping and driving policy, it's very diverse. There's a diverse set of workloads. Not everything is deep learning. So a successful chip is a chip, or a successful system on chip is one that provides you cores that are excelling in different types of workloads. And this is what IQ5 does. And the power consumption is very, very small, and it's very important to have power consumption. This is part of our scalability premise, because at the end of the day, these things should sit in a car. And most likely, these cars are going to be battery operated. And you'd like the energy of your battery to be used to propel you forward and not to run your chips, right? So power consumption is very, very important. Now, together with Intel, I put here where we are harnessing the power of Intel. So we took the IQ5, which again is being sampled in a few months. We have hundreds of people from Intel working with us to open it to third parties, which we call this an open IQ5. So this is something new. This is something that as Mobileye we have never done. Mobileye was always a closed system. You buy our chip with our software, and it's just like Apple, right? It's a closed garden. We are now opening up our offering to offer also open compute with different kinds of partnerships. You can have a turnkey system from us, which is our system on chips and the software, all the stuff that I've shown you before. You can have a semi-turnkey solution, which is, say, the perception is coming from us, a chip with the perception. The fusion and driving policy could be joint work on an open IQ5 or an Intel Atom architecture, or you can just buy from us open compute completely. Not a single open compute and all the libraries, not a single line of code, a functional line of code from our side. So opening up the IQ5 is a big effort, and is going to come out together with the launch of the first samples of the IQ5. We began a new effort of an IQ6, which will be a 50 tera operations per second. It will come a year and a half later after the IQ5, and this will have Atom architecture, Atom CPUs architecture. And you can see that the hardware is very economical. It has 2 IQ5, so this is hardware sufficient for running level 4 automation, 2 IQ5s, one to do the perception, the other one to do the fusion and policy, and a third Intel Atom chip, which will be either Denverton or Xeons, and then there is a fail operation channel. The radars and lidars, they come into the 2 IQ5 chips. So this is very economical in terms of the silicon wear, and of course the cost and the power consumption. Together with Intel, we're building a fleet of 100 vehicles, and yesterday at the keynote, the first car that you saw there, everything is placed in a very discrete manner. The cameras, the radars, the lidars, all the silicon hardware is there, and it is ready to be deployed. We have already 33 vehicles being manufactured, and we'll ramp up till the end of the year to 100 vehicles for the purpose of data collection, for testing, and customer support. And then together with Intel, we're building data centers. We're building a data center of 250 petabytes to hold data that we collect for validation. It's not only for development and training, but also for validation. So all of these things would have been very difficult to do as Mobileye is a company of 1,000 people. So this is really harnessing the power of being part of Intel. In terms of partnerships, we have level 3 production, serious development, starting with 2019 with all the car manufacturers here. So these are not research activities or PR activities. This is real production with real dates coming out starting on 2019. We have level 4 production. These are strategic partnerships targeting 2020 and beyond. BMW, which was announced last year. This is the Vulcan project. Fiat Chrysler joined a few months ago. We announced yesterday SAIC, and NIO has been with us also. We announced that last year. We have 3 OEMs in ongoing sourcing decisions. I hope that in the near future we'll be able to reveal who those OEMs are. And then we have, those are strategic partnerships. It means we and the OEMs, we are doing the perception, the driving policy, and the fusion is done as a kind of a joint cooperation. Then we're working on a turnkey solution. One of them is with our partner Aptiv, formerly Delphi, the CSLP platform. We demonstrated last year our joint activity. This year, Aptiv has a very, very cool demo together with the Lyft. And we're working together both in getting customer commitments to the turnkey solution, and we have been getting great success. And our internal fleet is also part of a turnkey solution that we'll be able to offer. Finally, the master plan of our activity is on one hand, is a turnkey solution where we provide the perception, driving policy, safety, all the safety layer, the multi-domain controller prototype, which has 2 IQ5s and an Atom architecture. And all of this is derived from our 100-car fleet. Then another type of partnership with the perception turnkey, which is an IQ5, where the other parts are on an open IQ5, either joint collaboration or completely by a third party. And then through Intel, completely open compute. Open IQ5, then returning Xeon, Altera, FPGAs as an open compute. Then we have the level 2 plus programs, which is the front-facing plus the map. This is starting 2019. Then we have REM as a data strategy. And finally, the RSS as a safety layer. Okay. I'll end here, and I'm happy to take questions.
We just have time for a couple, and then we need to clear the room pretty quickly so we get invited back for next year. Yeah, go ahead, sir. We have a mic coming right to you.
Thanks very much. David Wong, Wells Fargo. Can you give us some idea of the dollar value per car from Mobileye products, traditional products, and the additional dollar value you expect to get because you fold in Intel's capabilities and Intel-based products?
Well, driving assist, the range goes from, say, $50 to $250 per car. Autonomous driving, we expect it to be in the few thousands. Small few thousands.
Yeah, one in the back.
Hello. I heard you saying earlier, Amnon, you were talking about the IQ4 and level 2 plus systems, and you said so since the IQ4 can detect stop lights and stop signs, you said it would be enhancing ACC with that information. Were you implying that vehicles would come to stop at intersections where there's a red light or stop sign with the IQ4 and level 2 plus systems?
So we have to separate when there is a map and when there isn't a map. If you have just the IQ4 and there's no map information, you can detect the traffic lights, you can detect the relevancy of the traffic lights. The problem is finding the stop line. Finding the stop line, if the stop line is visible, you can see it only 10, 20 meters, and that's not sufficient for a smooth stop. So what you can offer, if you want to be very conservative, what you can offer is a warning of a red light and not stopping of a red light. But if you have a map, the stop line position is part of the map, because through crowdsourcing, you know where the stop line is, and that you can provide another level of performance where you can actually stop. If you are first to the traffic light, you can stop at a red traffic light. Okay, maybe one more question.
Yeah, we'll take one
Yeah,
more.
go ahead.
Go ahead.
Excuse me. I had a chance to speak with some of the Volocopter folks this week, and I know that they were really excited to work with Intel in the future because of some of the companies like Mobileye that are under the Intel umbrella. Are there companies like Volocopter under the Intel umbrella that you're excited to work with as well, including Volocopter?
I think, this vertical flight machines, it's also part of the future. Cities are becoming more and more dense. If you want to arrive to the airport on time, taking a taxi is kind of risky. You can have this kind of a volocopter that will take you, and the numbers show that these machines can be built at the cost of a car. So it could come to a cost of just ordering an Uber and to fly to the airport. So I see lots of promise in these kinds of initiatives, and also making these machines fly autonomously is also a great challenge. I think it's a different challenge from autonomous cars. On one hand, it's simpler. You don't need to negotiate with anyone when you're flying in the air. But the flight regulations are much more stringent than the FAA is much more stringent than driving regulations. So it's more difficult in that area. But there's lots of technology to be developed in order to automate that, and lots of data. The data story here is also quite significant. So we are excited that Intel sees Volocopter as a driver, as an engine for the future, and we'll be happy to work with them.
Okay, thanks everyone. Have a good CES.
Thank you.